So we're going to look first of all at topic 1 of the physics specification. So this is common to both double and triple science physics. So P1 topic 1, concentrating on conservation and dissipation of energy. So basics first of all, we've got our energy stores, how energy is stored into its different types. So we've got chemical, which are things, chemical energy is what's stored in batteries and fuels. Kinetic, which is a moving object, so obviously the faster an object is moving or the heavier the object, it's going to have more kinetic energy. Gravitational potential, so something that's been acted on by a gravitational field will have gravitational potential energy. The higher up it is, the more mass, or the stronger the field, means it's going to have more gravitational potential energy. Thermal, hotter something is, the more thermal energy it's going to have. Magnetic, there's a magnetic field between objects. Nuclear energy, which is the energy stored within the atom. Elastic potential, which is something like a spring that's been compressed or extended in some way, or a string that's been stretched. And electrostatic, so think of sticking a balloon to a wall on an object that's got an electrostatic field between it, electric field between it. Then we've got our pathways. We've got to be clear here. Stores, this language, these energy is stored in this format. Our pathways is how we go in between these stores. So if we're going from one store to another, we have to be going via a pathway mechanism. So what are these pathways, or what are these transfers? So we've got radiation, which could mean light, it could mean sound, but it could also mean another form of electromagnetic radiation, like an X-ray or microwave. That is a pathway as well. But mainly it's going to come under light and sound. Heating, so not to be confused with thermal energy. If something has a store of energy, it has some temperature, it has some heat energy in it, it has now got a thermal store. Heating is when there's a temperature difference between objects and you are heating something up. You are transferring energy to that object. It is a different temperature to its surroundings, for example. Electrical, so energy transferred through electrical. You don't say electricity, you have to use the word electrical energy. And then mechanical. Now this is the one that seems to be causing the most issues with pupils and their understanding. Mechanical is when you are essentially you're exerting a force on something. So are you having to push something? Are you trying to turn something? There's a gear turning something. Or maybe you're exerting a force to lift an object through, for example, a gravitational field. So if you were lifting an object off the ground, that would be via the mechanical pathway. So let's have a quick look at an example of this. Classic example is like a battery operated torch. Well, if there's a battery in there, well, which one of our stores does it start with? Oh, well, that would be a chemical store of energy. And it's going to go via the electrical pathway. And then we're going to transfer energy out via our light pathway. We'll go into later, well, is it all through to light pathway, or does something else happen? Is there some energy wasted? Another example could be like a wind-up toy or a jack-in-the-box or something like that, where maybe you've got some elastic potential energy. So you've got elastic potential energy stored in the compressed spring. As that compressed spring moves, it exerts a force once it's released onto the toy. Well, that would be via the mechanical pathway. And then the toy would have a kinetic store, or say you were talking about for when the toy got to the top and then stopped. That would be a gravitational potential. And same thing if you were talking about throwing up a ball into the air. Well, it would have some kinetic energy that you'd give it at the start. It would then go to the top until, before it falls back down, it's going to stop instantaneously in the air, which would mean it has gravitational potential energy. And this would be via the mechanical pathway. So next we need to look at, well, if energy is transferring between these stores via pathways, well, how much energy is transferred? What happens? How do you quantify it in some way? So we need to bring in one of our laws of physics, conservation of energy. Energy cannot be created or destroyed. It's one of the classic laws. You might, even before you'd study this, you might have heard of that. Energy cannot be created or destroyed. So what do we actually mean by this? We need to keep thinking and linking it back to our energy stores that we talked about. If you think of a ball, for example, that you're on the top of a cliff, let's say that the ball was at some height there. So you're at the top, so it's got some gravitational field acting upon it by the Earth. So let's make up that it's got 1500 joules of gravitational potential energy. Now, due to this law, and a lot of questions in your GCSE physics paper will assume that this law always acts, but they will assume that you need to know this law without even mentioning it. So what that means is they may say to you, well, how much kinetic energy has this ball got before it hits the floor? So if it's fallen from the top of the cliff, how much energy does it have at the bottom? How much kinetic energy does it have at the bottom if it's got 1500 joules of gravitational potential? But maybe they haven't, we're going to see later on that there's an equation to work out kinetic energy. But what if they haven't given you anything to actually work it out? They haven't given you any numbers about the mass of the ball or anything like that. Well, you just need to think that, well, wait there, energy cannot be created or destroyed. If it's got 1500 joules at the top of the cliff, that must mean now that energy has been transferred. The pathway would be the mechanical pathway, and it's been transferred to the kinetic energy store. So now at the bottom, just before it hits the floor, it must have 1500 joules of kinetic energy just before it hits the floor. We know that from our law of conservation of energy. Now, you could be thinking though, well, wait there, this doesn't really make sense. If we think of, I don't know, something like a roller coaster, or if we think of rolling a ball down a dip, well, due to that thought process, well, surely if we roll the ball down here, surely our conservation of energy has got to have so much energy here. It's going to go to kinetic, and it's going to go back up to gravitational potential. So surely it should reach the other side over here. Now, we all know that in real life that doesn't happen. Because for this law to work, it must be a closed system, or what we would call an isolated system. Well, this would not be a closed system because the ball is interacting with its surroundings. So what we get is energy dissipation. We are not breaking this law. The law still holds, but there is some energy being dissipated from the ball to the surroundings. To surroundings, you must use that terminology, surroundings. So this would be not an isolated system. It's not a closed system. So the mechanisms that energy dissipation can occur through are through things like friction, or things like air resistance. So lots of mechanical things would have resistance. Lots of things would have air resistance acting upon it. So that would cause heating of surroundings, heating transferred into surroundings, or heating of the object itself. Okay, so if there's friction acting on that ball, well, the ball would very slightly heat up, and the friction caused by it rubbing against the floor will slightly warm up as well. That would cause energy dissipation. So for a lot of times for calculation questions, you're not perhaps including this. You're just assuming that it's a closed system, and you can make this approximation that due to the law of conservation of energy, if you start with some amount of energy, it's going to end up with the same at the end. But other types of questions, you may be having to think about energy dissipation. That leads us to energy efficiency. So let's go back to that example of the torch. Okay, we said that there was a certain amount, you could have chemical energy in the torch, in the battery of the torch, and you're going to have a certain amount of energy. Energy efficiency was how much, well, what proportion of the chemical energy that you're inputting in here is coming out to what is meant to be as useful energy. So the energy efficiency equation is one that you need to learn, and it's efficiency equals the useful energy output divided by the total input energy. So for example, if this was putting in 200 joules of chemical energy, and you were only getting out, let's say it was quite an inefficient light, inefficient torch. That means you may only have, say, 50 joules of light energy with 200 joules of chemical. Well, what that means there, well, there must have been, due to our law of conservation energy, we know that something's gone wrong here. Don't appear to be conserving energy. But that's because, oh wait there must be some of that energy dissipation. So that must mean there's 150 joules of wasted energy going on here. Now, the pathway here would be the electrical pathway we said between the chemical and then before the light leaves. So what that means is a lot of the time, whenever you have electric current, there would always be at least some heating. So what we've got is heating here, and you'd have 150 joules of wasted heat energy. So sometimes they may tell you the heat energy or might tell you the wasted energy and not tell you the useful. You need to think, well, how much useful must there be? Say they told us there was 150 wasted. Well, we must know if there's 200 to start with, there must have been 50 useful given out on the other end. We could then put these numbers into our equation here. So we would do useful, which would be 50, divide by the total input there, which would be 200. And that would give us 0.25. So if we want to convert that into a percentage, we do times by 100, and we would get 25% efficiency. So this equation is literally just working out a percentage. Now a key point is that nothing can be 100% efficient. Nothing can be more than 100% efficient. If you do this calculation and you get a number more than 100%, you know you've done something wrong. You've put your numbers in the wrong way around. So go back, have you confused what was the input energy and what was the wasted energy.
So next we're going to look at
the energy equations, because some of these energy stores that we talked about just now, we need to know the equations of them and how we can calculate the equations. Now, an important fact to remember is that in your GCSE physics paper, 30%, a whole 30% of the paper will be maths-based questions. Now that is absolutely massive. If you look at last year's grade boundaries, you can see that some of the grade boundaries, can't do it off the top of my head, but I think there was literally only in the 60 odd % range for the high grades of 7, 8s and 9s. I think a 7 was literally only like 50% or something. So if you nailed the maths questions in your physics paper, you would have done extremely well without barely even trying very hard on the actual content and the understanding questions. So understanding these physics equations is absolutely imperative to your success in the exam, and it's a good way of getting guaranteed marks. You're not having to rely on making a mistake about forgetting out a keyword or something. You're literally just remembering the equation, understanding the equation, and applying it properly. So what are some of the energy equations that we need to know? So first one is kinetic energy. So kinetic energy would be energy is always in joules. You have to use a capital J for joules. Equals mass. Mass is always in kilograms. So remember, if they give it to you in grams, there's 1,000 grams in 1 kilogram. There's 1,000 grams in 1 kilogram. So if they say something's 300 grams, right, I need to divide by 1,000, that would be 0.3 kilograms. You need to make sure you convert that before you put it into this equation. So the next thing there is V, which is velocity. So the units of velocity are meters per second. And then we've got divide by 2. So you may have seen this equation in the other format of kinetic energy is a half times mass times velocity squared. Well, this is the same, this is writing it out is the same way, you're just dividing it all by 2. A half times mass times velocity squared is the exact same as mass times velocity squared all divided by 2. It's the same thing. I would advise you to learn it and write it out this way, because people tend to make less of a mistake when rearranging it. You do need to be able to rearrange these equations for a higher tier. It came up a lot, it comes up a lot on the paper. So how would we rearrange this equation? So say let's do the one that people find the most difficult. Say we're going for velocity. So we need to do the opposite if we want to get velocity on the own. So at the minute it's all divided by 2. So I need to do the opposite. So I need to multiply by 2. So I'm going to have 2 times kinetic energy equals mass times velocity squared. Well, now we've got mass times velocity squared, and we want the velocity. We want to work out the velocity of this object. So what we do, we need to get rid of the m first. So we need to then multiplying. So we do the opposite. We would divide. So we'd have 2 times kinetic energy divide by mass equals velocity squared. Right, now we just need to get rid of the squared. So we're going to square root it. So we end up with square root of 2 times kinetic energy over mass equals your velocity there. Then you simply plug in the numbers into the calculator, making sure that you remember to convert the units. Okay. Next one is gravitational potential energy. So pupils tend to not struggle as much with this one. Again, gravitational potential energy is a form of energy, so it's always going to be in joules, capital J. Mass is going to be in kilograms. G, gravitational field strength. Acceleration due to gravitational field strength is going to be, that is a number that you need to memorize. They may not give you that in the exam. So that is equal to 9.8 or 10. You can use either, really. Height has got to be in meters. Okay, so if they've given it to you in kilometers, same thing as before. Well, if they say that something is 2.2 kilometers, well, there's 1,000 meters in 1 kilometer. So if they say it's 2.2 kilometers, well, you need to know that that's 2,200 meters. Then you could use that in the equation. So let's try and rearrange this now. And let's say they gave you some gravitational potential energy, they gave you some mass, and they wanted you to work out the height. So what we need to do, write out the equation. Always write out the equation first. Show the examiner what you're doing. Show the examiner that you know your equations. So we're going for height. So I need to, well, these are multiplied by each other. So all I need to do is get rid of the m and the g. So they're multiplied by each other. So I can just divide by them. And it would just be gravitational potential energy divide by mg equals h. And then I can plug my numbers in. I've shown the examiner that I can rearrange the equation, so even if I make a mistake now of putting the numbers in, I would still write the numbers in to my exam exactly as I put in my calculator. So I haven't got an actual question here, but if say it was 500 joules or whatever, divide by a mass of 10 kilograms times by the 9.8, I'd write that down on my exam. I'm going to do another video where we look at lots of examples of all these energy questions that we've been talking, all these energy content we've been talking about. Now, next equation. The good news is that this is one that you don't actually need to memorize. They will give you this one in the formula sheet in the exam. So this is the elastic potential energy one. So this was like, well, what if you've got a spring that's being compressed? This is elastic potential energy. So yeah, you got it. The units are going to be in joules. So we've got K here. Now K is the spring constant. K is the spring constant. I'm not going to go massively into that now. I'll do that in the different topic. But the spring constant basically refers to the stiffness of the spring. How much force do you have to exert on the spring for it to stretch or compress? So if you have to exert a lot of force, it's going to have a higher spring constant. It's going to be like a very strong spring. Now X refers to the extension or the compression of the spring or whatever it is you're talking about. Now this has got to be in meters. Okay, now this is another thing that they are going to try and catch you out. They may give it to you in millimeters. They may give it to you in centimeters. So if it's given to you in centimeters, well, there's 100 centimeters in a meter. So if they say it's something like 80 centimeters, well, you need to go, well, that's 0.8 meters. If they've given it to you in millimeters, there's 1,000 millimeters in a meter, so you need to divide by 1,000 to get it in meters. And then don't forget the divide by 2 there as well. So rearranging this is going to be a similar thing to the kinetic energy formula is in the same type of format. Let's rearrange for K on this one. So we've got elastic potential energy equals kx squared over 2. Let's say we'll go for K, so I want to get rid of the 2 first. So I'm going to multiply through 2 times EAL equals kx squared. Then I want to get rid of the x squared, so I'm going to then multiply it, so I divide through by it. And then we've got spring constant there, if the question was asking me to calculate the spring constant. So, what other equations have we got to learn for this topic? So, other energy equations we've got to look at is the work done. So, we need to talk a little bit about work done. What do we mean by work done? Work done is energy transferred. So if energy is changing between types, if energy is transferring between energy stores, I should say, not types, sorry, energy stores, that means there's been energy transferred. Okay. Now, well, what does that mean? Well, that essentially means that work done is energy. So it is how much energy has been transferred. So that means it's units or joules. Okay. So what do we actually mean by energy transferred? Well, let's look at a quick example. Let's say here, they may just say to you, oh, a car has a kinetic energy of 5,000 joules. It came to a complete stop. How much work has been done by the brakes? Now, you could think some people would be sitting at that question thinking, oh, wait there, I know my equation, I've done my hard work, I've learnt my equation for work done. That's force times distance. Oh, but they haven't mentioned force or distance in the question. So, what do I need to do? Well, you just need to think of your actual definition of work done. Work done is energy transferred. Well, if they had 5,000 joules of kinetic energy, well, where's that energy gone? Well, if it's stopped, well, it's no longer got kinetic energy. Well, think about what happens when the car brakes. It would have gone to the heating of the brakes. It would have heated up the brakes. And that 5,000 joules of kinetic energy would have gone to heat on the brakes. But that still means that the work done by the brakes, well, there's been energy transferred from kinetic to heat to thermal. So that means the work done is simply 5,000 joules without having to do any calculation at all. So let's look at the actual equation though. So force is in newtons with a capital N. Distance is in meters. Be careful with this distance though. It's the distance in the direction that the force is acting upon. So for example, you're pushing a box, you're applying a force that direction, so the distance travelled is in this direction. Okay. An example of this is, well, what if you had a racetrack and you were going around the racetrack? Well, if you start here and you've ran all the way around the racetrack and you end up back where you started, oh, well, wait there. Surely you've covered loads of distance, but oh, well, the distance travelled is, if you ended up back here, well, is there no distance travelled? So therefore, your work done would be 0, even though you've got ran all the way around. So really, you have done a distance. So what you've got to think of, or what it means is distance in the direction of the force. So as you're running this way, the force is going, you're applying force on your feet to get forward in this direction, and then this direction, and this direction, and this direction. So if we added up all these distances, well, you have done work done. And if we added all that work done, you've done the work done across the whole of the racetrack. So, next one would be power. Power is energy transferred divided by time. So power, the unit is watts. Energy, we now know, is joules. Time is always in seconds for physics, always in seconds. Again, if they give it to you in minutes or hours, think about how many seconds are in a minute. If they've given it to you 3 minutes, well, I need to convert that into seconds. If they're giving it to me in kilojoules, do I need to convert it to joules first? So let's think about what that means. If a watt is joules and seconds, what that actually means is 1 watt of power is equal to 1 joule per second. So 5 watts would be 5 joules per second. So power is energy transferred over time. Well, another form of this equation, it looks like there's loads of equations to learn for your physics, but actually, when you break some of them down, they're very similar equations. Well, energy transferred, well, we just said energy transferred was work done. So another form of this equation is, instead of saying energy transferred, you could say work done over time. Okay, so you've got power is work done over time. What this could also mean is, maybe they were asking you to work out the power, and they haven't given you energy, or they don't seem to have given you work done. Well, have they given you something like force and distance, so you could then work out the work done, and then work out the power? If we go back to the other equation that we looked at, so for example, we said that gravitational potential energy equals mass times gravity times height. This is a similar thing going on here. Gravitational potential energy, mass times gravitational field times height. Well, mass times acceleration due to gravitational field strength is the same as weight. Weight is equal to m times g. So this, you can rewrite this equation if you wanted into w times height for weight. It's a similar thing. It looks like there's lots and lots of equations for us to learn, but it's not so bad. Lots of these equations are very similar. We've got our power one. Again, if we think of that efficiency one we talked about. So we said that efficiency was useful energy output over total energy input. We could apply the same equation, but instead of talking about energy, we could talk about power. So we could say useful power output divided by total power input. It's the same equations. And that's the first topic of the energy. There's 3 energy topics. It's such a huge topic that it's split into 3 mini topics. So we'll go on to the second 2 later.